Turn off the lights, my friend. I am HyperSleep Logs. Together, we're stepping into the deep mysteries of the cosmos. Our journey begins, right now. The edge of everything, black holes, the holographic universe, and what lies beyond the end of time. Let me tell you about the moment physics broke. Not in the dramatic way you might imagine. No explosion, no announcement, no single paper that everyone agreed was the breaking point. It happened slowly, over decades, as two of the most successful theories in the history of science kept arriving at conclusions that could not both be true. General relativity, Einstein's theory of gravity and spacetime, and quantum mechanics, our theory of the very small, each worked brilliantly in its own domain. Each made predictions confirmed to extraordinary precision. Each was a triumph of human reasoning. And they directly contradicted each other. Nowhere is that contradiction more violent, more unavoidable, or more consequential than at the center of a black hole. This is the place where both theories must apply simultaneously and where they produce answers that cannot be reconciled. It is the place where physics breaks down and admits, honestly, that it does not know what happens next. But here is the thing, the breakdown is not just a technical embarrassment. It is a clue. The place where our best theories fail is also the place where the deepest truths about the nature of reality might be hiding. And the strange, counterintuitive ideas that have emerged from decades of physicists wrestling with black holes have led us somewhere genuinely astonishing, to the possibility that the universe itself, everything you see and touch and are, is not what it appears to be. Let me take you there. Step by step. No shortcuts. Because the destination is worth the journey, and the journey requires understanding the terrain. Start with what a black hole actually is, stripped of all the mythology and science fiction. A black hole is a region of space where gravity is so strong that nothing can escape it, not matter, not energy, not light. The boundary of this region is called the event horizon. It is not a physical surface. There is no wall there, no membrane you would feel if you crossed it. It is just a mathematical boundary, a point of no return, beyond which the geometry of spacetime curves so severely that all possible paths lead inward. How does this happen? Through the compression of matter to extraordinary density. A star many times the mass of our sun collapses at the end of its life. The outer layers blow off in a supernova. The core, suddenly unsupported, collapses under gravity. If the core is massive enough, no force in the universe can stop the collapse. Electrons cannot resist it. Neutrons cannot resist it. The core compresses to a point where our equations produce infinities and stop working. We call that point a singularity. So at the end, a singularity of theoretically infinite density and zero volume, surrounded by an event horizon, the point of no return. Outside the event horizon, spacetime is curved but navigable. Inside, it is so severely warped that every path in every direction leads to the singularity, including forward in time. This is the first genuinely mind-bending thing about black holes. Once you are inside the event horizon, the singularity is not a place you are moving toward. It is a moment you are moving toward. It is your future. You cannot avoid it for the same reason you cannot avoid next Tuesday. Think about that carefully. In ordinary life, space and time are different things. You can move freely through space in any direction. Time flows in one direction only, forward, and you have no control over it. Inside a black hole, these roles swap. The spatial direction toward the center becomes time-like. The singularity becomes inevitable not as a location but as a moment. General relativity makes this prediction with mathematical precision. The geodesics, the paths of shortest distance through curved spacetime, all terminate at the singularity. There is no trajectory, no matter how energetically chosen, that avoids it. And this is where physics runs into its first crisis. The singularity is not a physical prediction. It is a failure of the theory. Infinite density means the math is not describing reality anymore. It means we have pushed the equations beyond their range of validity. What actually happens at the center of a black hole, we do not know. General relativity cannot tell us. We need a different theory, presumably a quantum theory of gravity that we do not yet have. Now let me take you to the second crisis, the one that gets really interesting. You are falling toward a black hole. From your perspective, you are in free fall. You do not feel any particular force. If the black hole is large enough, you might not even notice the moment you cross the event horizon. You cross it, and nothing spectacular happens immediately. But here is what an outside observer sees: they watch you fall. As you approach the event horizon, you appear to slow down. This is gravitational time dilation, one of general relativity's predictions. Clocks run slower in stronger gravitational fields. Deep in a gravitational well, time passes more slowly than it does far away. Near the event horizon of a black hole, this effect becomes extreme. From the outside, you appear to freeze. Your image redshifts, the light coming from you stretching to longer and longer wavelengths. You become dimmer and dimmer, redder and redder, and you never quite cross the event horizon. You appear to hover there, infinitely slowly approaching but never arriving, fading into the dark. From your perspective, you cross normally. You fall through. Time passes normally for you. Both perspectives are valid. Both represent real experiences. And they are completely irreconcilable in terms of ordinary common sense. This is not a contradiction in the theory. It is a feature of what spacetime actually does. But it sets up a problem that has occupied physicists for nearly half a century, a problem called the black hole information paradox. Here is the paradox. Quantum mechanics has a law, an absolute law, that information cannot be destroyed. The quantum state of a system can evolve and transform, but the information encoded in it cannot be lost. If you know the exact quantum state of a system at one moment, you can theoretically calculate its state at any other moment, past or future. The universe keeps perfect books. Now, you fall into a black hole. Eventually, the black hole evaporates. Stephen Hawking showed in 1974 that black holes are not completely black. Through a quantum effect near the event horizon, they slowly radiate energy, what we now call Hawking radiation. Over an inconceivably long time, trillions upon trillions of years for a large black hole, they radiate away all their mass and disappear. What happens to the information you carried in with you? If Hawking's original calculation was correct, the radiation is perfectly thermal, it carries no information. It is random noise, like the static on an untuned radio. The information you brought in is gone, permanently destroyed. But that violates quantum mechanics absolutely. It says the universe can lose information. And if the universe can lose information, then quantum mechanics is wrong at a fundamental level. Either general relativity is wrong about what happens inside black holes, or quantum mechanics is wrong about the conservation of information. Both theories are among the most precisely tested in the history of science. Both cannot be simultaneously correct in their current forms. This is the information paradox. And the attempt to resolve it has led to some of the most radical rethinking of the nature of reality in the history of physics. Let me tell you about firewalls. In 2012, a group of physicists, Almhiri, Marov, Bolchinski, and Sully, published a paper with a deeply disturbing conclusion. If information really is preserved, if it has to escape from the black hole somehow, then something has to happen at the event horizon to make that possible. Their calculations suggested that what must happen is dramatic. The event horizon becomes a wall of high-energy radiation. A firewall. Anything that crosses the event horizon is immediately incinerated. This resolved the information paradox in the most violent way possible, by saying that the smooth crossing of the event horizon that general relativity predicts simply does not happen. Infalling matter hits the firewall and burns. The information is encoded in the radiation. But this creates its own problem. It violates what physicists call the equivalence principle, one of the foundations of general relativity. The equivalence principle says that free-falling observers in a uniform gravitational field should not be able to distinguish their situation from floating in empty space. An observer crossing a sufficiently large event horizon should not notice anything special at the moment of crossing. The firewall violates this. It says crossing the event horizon is not smooth. It is catastrophic. So we have three options, and they're all bad: violate quantum mechanics, violate general relativity, or violate the equivalence principle. Pick your poison. Every resolution creates new problems. The paradox has swallowed several generations of brilliant physicists and has not yet released them. But in the struggle to resolve it, something extraordinary has happened. Physicists began thinking about what information preservation really requires, and they arrived at an idea that is perhaps the most radical proposal about the nature of reality ever seriously entertained by mainstream physics: the holographic principle. The idea was proposed in the 1990s by Gerard T. Hooft and Leonard Susskind, building on earlier insights and later connected to string theory by Juan Melda-Sena's AD/CFT correspondence. The core claim is this: the information content of any region of space is not proportional to the volume of that region, but to its surface area. Think about what that means. You have a box. In ordinary physics, the amount of information you can store in that box scales with the volume. Double the volume, double the information capacity. This seems obvious. Information is stored in the things inside the box. But the holographic principle says, the maximum information content of the box is proportional to the area of its surface, not its volume. This is a completely non-obvious claim. Why would the surface of a region limit the information content of its interior? The mathematics of black holes gives us the answer. The entropy of a black hole, which measures its information content, is proportional to the area of its event horizon, not the volume inside. The surface area. Bekenstein and Hawking derived this result from thermodynamics and quantum mechanics. The entropy formula works. The black hole's information content scales with area, not volume. If this is true for black holes, might it be true generally? Might it be that the information describing everything inside any region of space is actually encoded on the boundary of that region? Meldesena's discovery in 1997 provided the most concrete realization of this idea. He found a precise mathematical duality between a theory of gravity in a certain curved space, technically anti-de Sitter space, and a quantum field theory without gravity on its boundary. The two descriptions were not just analogies. They were mathematically equivalent. Every process in the bulk space had a precise description on the boundary surface. They were the same thing, viewed from different perspectives. This is the holographic duality. The universe has a description in terms of three-dimensional gravity and fields moving through space. But it has an equally valid, mathematically equivalent description in terms of a two-dimensional theory on its boundary, with no gravity at all. Which one is more real? Neither. They are dual descriptions of the same physics. But if you ask which is more fundamental, the holographic principle suggests the boundary description is. The two-dimensional theory without gravity is simpler, more complete, free of the singularity problems that plague gravity. It is the deeper description. And if that is right, the implications are staggering. Our three-dimensional experience of reality, the depth, the volume, the sense of being embedded in a space that extends in all directions, might be an emergent phenomenon. It might not be fundamental. What is fundamental might be a two-dimensional structure, something like a vast information processing surface, and what we experience as three-dimensional spacetime is something that emerges from that, something projected, like the image from a hologram. Let me be careful here, because this is where people sometimes jump to conclusions that the physics does not support. The holographic principle does not mean reality is an illusion in the sense that science fiction usually means. It does not mean we are characters in a simulation, or that the physical world is not real. Your pain when you stub your toe is real. The star that exploded 12 billion years ago is real. What it means is something more subtle and more profound, that the way we naturally parse reality into three-dimensional space filled with objects may not be the most fundamental description. The most fundamental description might be lower dimensional, and the three-dimensional world emerges from it. This is what physicists mean when they talk about spacetime being emergent. Not that it does not exist, but that it is not the bedrock level of description. There is something more fundamental, and spacetime arises from it, the way temperature arises from the average kinetic energy of molecules. Temperature is real. Heat is real. But at the deeper level, they are properties of something more fundamental. Now let me take you somewhere even stranger, the end of time. We have established that black holes evaporate through Hawking radiation. They are not eternal. Given enough time, every black hole will radiate away its mass and disappear. The timescales involved are incomprehensible to ordinary human intuition. A black hole with the mass of our Sun would take 10 to the 74th power years to evaporate. The observable universe is only about 14 billion years old. The time required for solar mass black hole evaporation is not just larger than the current age of the universe. It is larger than the current age of the universe by a factor so enormous that writing it out in ordinary numbers would take more than the observable universe to store. And the supermassive black holes at the centers of galaxies, billions of times more massive, would take proportionally longer. We are talking about timescales so vast that they make the current age of the universe seem like the first millisecond after the Big Bang. But eventually, they all go. Every black hole. And with them goes the last large-scale structure in the universe. Long before the last black holes evaporate, the stars have all burned out. The last red dwarf star will extinguish itself in about 10 trillion years. The protons that make up ordinary matter may themselves decay, over timescales of perhaps 10 to the 36th years. By the time the last black holes are evaporated, the universe is almost perfectly uniform, almost perfectly cold, almost perfectly dark. This is the heat death. The state of maximum entropy, where no energy gradient exists, no work can be done, no change can happen. Thermodynamics tells us this is where the universe is heading. The second law, entropy always increases, describes an arrow of time pointing toward a state where change becomes impossible. When change becomes impossible, time becomes meaningless. Not because a clock stops, but because there is no process by which you could distinguish one moment from the next. The distinction between past and future requires some process that runs in one direction. In the heat death, there are no such processes. Does the clock of the universe stop? Does time end? Or does it simply become undefined, the way asking what direction is north at the North Pole becomes undefined? Physicists are not in agreement. Some argue that time is fundamental and continues even when nothing changes. Others argue that time is relational, defined by the relationships between events, and without events, there is no time. The question touches the deepest issues in the philosophy of physics. But here is where the holographic principle comes back in, and where things take a genuinely extraordinary turn. If information is preserved, and the holographic principle says it must be, then the Hawking radiation from every black hole, however featureless it appears, must encode everything that fell into that black hole. The information is not destroyed. It is transformed, scrambled beyond any practical ability to decode, but preserved. And if the universe as a whole obeys a holographic principle, then the information describing everything that has ever existed, every particle, every event, every thought, every star, every civilization, is encoded somewhere. On some boundary. In some description. What happens to that information when the universe reaches heat death? Some physicists have speculated about quantum fluctuations. In quantum mechanics, even the vacuum is not empty. It fluctuates, constantly, with particles appearing and disappearing on timescales too short to observe. In a universe at heat death, these vacuum fluctuations continue. And if you wait long enough, vastly longer than the current age of the universe, some incredibly rare fluctuation might produce a large-scale ordered state spontaneously. This is called a Boltzmann brain scenario in its most extreme form, a random fluctuation producing a conscious brain in empty space. But you can imagine less extreme versions. A random fluctuation producing a patch of low entropy, a pocket of order, something from which new complexity might grow. You can even imagine, though this is deep speculation, that the information encoded in the holographic description of the universe could somehow seed a new quantum event. A new Big Bang. Not from nothing, but from the information that survived the previous universe's heat death. This is the idea of a cyclic universe, not in the simple sense of a universe that bounces, but in the sense of a universe that encodes its information and uses it to initialize the next cycle. We would be living in a chapter of a longer story, and the information we generate, the memories we form, the patterns we create, would in some sense persist beyond the death of this universe and seed the next. Is this true? We have no idea. It is speculation built on speculation, philosophy built on the shakiest foundations of quantum gravity that we do not yet have. But it is grounded in real mathematics, in real physical principles. The holographic principle is real physics. Information conservation is real physics. Quantum fluctuations in the vacuum are real physics. The connections between them that lead towards cyclic ideas are made by real physicists doing real calculations. The destination is extraordinary. But the route to get there is not mysticism. It is the hardest, most precise science we know how to do. Let me pull back now and talk about what all of this means for how we understand our own existence, because the personal implications of these ideas are not trivial. Start with time dilation. We know, from general relativity, that time passes at different rates in different gravitational fields. This is not a metaphor. It is a measured fact. GPS satellites have to account for time dilation. They run slightly faster than clocks on Earth's surface because they are higher in Earth's gravitational field. Without corrections, GPS would drift by kilometers within days. Near a black hole, this effect is extreme. A spaceship hovering just outside the event horizon of a supermassive black hole would experience time almost stopped from the perspective of a distant observer. For every second that passes for the ship, millions or billions of years might pass in the rest of the universe. You could, in principle, use a black hole as a time machine. Not to go backward, but to jump forward. Dive close to a massive black hole, orbit for what feels like a short time, then return to find that the universe has aged enormously. This is physics, not science fiction. The equations allow it. Whether the engineering is possible is another question, but the physics says it is not forbidden. Now think about the event horizon itself. The fact that, from the outside, anything falling in appears to freeze, to slow down infinitely, to never quite cross the boundary. If that seems strange in the abstract, make it personal. Imagine watching a friend fall into a black hole. They wave as they fall. From their perspective, they cross the event horizon, fall inward, and eventually reach the singularity. All in some finite time by their clock. From yours, you watch them approach. They slow down. Their image redshifts. They never quite disappear. They hover at the boundary, frozen, fading. You never see them cross. Which experience is real? Both. The universe has arranged things such that both descriptions are correct, and they apply to different observers. There is no fact of the matter about whether your friend has crossed the horizon. It depends on who is doing the asking. This is not a quirk. It is a fundamental feature of spacetime, and it carries a quiet philosophical implication, our intuitive idea of a shared, objective present, a single moment that everyone exists in simultaneously, is not supported by physics. The universe does not have a single clock. It has many clocks, running at different rates, with no privileged master clock that everyone agrees on. Einstein showed us this over a century ago, but the full implications have been slow to sink in. There is no universal now. There is only the local now for each observer. And near a black hole, the difference between local nows becomes dramatic. And then there is the information paradox, which carries its own philosophical freight. If information is conserved, if nothing about you is ever truly destroyed, then in some precise physical sense, nothing is ever completely lost. The atoms that make you up will eventually be recycled into stars and planets and perhaps other forms of life. But even beyond that, the information encoded in those atoms, the specific pattern of your quantum state, is preserved in some form. This is not personal immortality. The information is scrambled beyond any practical recovery. You would not experience continuity. But in the deepest physical sense, the information that made you you is not erased from the universe. It is transformed, redistributed, hidden in the correlations of Hawking radiation and quantum fluctuations. Whether this should matter to us, whether it provides any comfort or carries any moral weight, is a philosophical question that physics cannot answer. But it is interesting to note that the physical universe, at its deepest level, appears to place extraordinary value on information. It encodes it. It preserves it. It cannot be destroyed. We are beings made of information. And the universe holds on to that information even after we are gone. Let me talk about Hawking radiation in more detail, because I think it is one of the most beautiful results in all of physics and deserves more attention than it usually gets. In quantum mechanics, the vacuum is not empty. It is constantly fluctuating, producing pairs of particles and antiparticles that appear from nothing and almost immediately annihilate each other. This is not speculation. It is measured. The Casimir effect, the attractive force between two metal plates in a vacuum, is caused by the difference in vacuum fluctuations inside and outside the plates. We have verified this in laboratories. Near the event horizon of a black hole, these vacuum fluctuations have a strange fate. Sometimes a pair of particles appears straddling the event horizon. One particle falls in. The other escapes. Normally, the pair would annihilate. But now they cannot reach each other. The infalling particle is captured. The escaping particle continues outward and becomes real radiation. Where does the energy for this real radiation come from? From the black hole itself. The infalling particle carries negative energy, by a precise accounting in the curved spacetime near the horizon, and the black hole loses mass equivalent to the energy of the escaping particle. The black hole gets lighter. Given enough time, it evaporates entirely. But here is the beautiful, troubling part. The radiation that comes out is thermal. It is the blackbody radiation of a body at a specific temperature, the Hawking temperature. And thermal radiation carries no information about what went in. It is like looking at the heat coming off a fire and trying to reconstruct what was burned. The fire scrambles the information. The heat carries only aggregate properties, temperature, not specifics. So when the black hole has fully evaporated, what has become of everything that fell in? The thermal radiation seems to say, gone, destroyed. But quantum mechanics says, impossible. This is the paradox in its purest form. The resolution, if there is one, requires that the thermal appearance of Hawking radiation is somehow illusory. That there are correlations hidden in the radiation, incredibly subtle, practically impossible to detect, but real. The information is there, encoded in the entanglement structure of the outgoing photons, invisible to any experiment we can currently perform, but not destroyed. This seems like a cheat. How can thermal radiation that appears random actually carry information? Because the appearance of randomness is perspective dependent. From the outside, looking at individual photons, the radiation looks thermal. But if you could measure the correlations between every photon over the entire evaporation lifetime of the black hole, you would find that those correlations encode the information. The book is scrambled, but all the words are still there. To actually decode it would require a computation of incomprehensible complexity. You would need to measure every photon, track every entanglement, perform a calculation that would take longer than the age of the universe. But in principle, the information is there. And if it is, then in some sense everything that has ever fallen into a black hole is still accessible, still encoded in the universe, still real. The ancestors of the universe, the stars and planets and living things that fell into black holes billions of years ago, are not gone. Their information persists, scattered and scrambled, in the correlations of photons slowly spreading through the cosmos. This is a strange comfort. But it is, if the physics is right, a real one. Let me talk about singularities, because they deserve more attention than they usually get in popular discussions of black holes. A singularity is not a thing. It is a failure of description. When the equations of general relativity produce a singularity, what they are really telling you is that they have exceeded their range of validity. The physics is breaking down. Something new is needed. This is not unique to black holes. Cosmology has a singularity too, the Big Bang. Our equations, run backward in time, produce a singularity at the beginning. A point of infinite density, infinite temperature, infinite curvature. And again, this is not a description of what was actually there. It is a signal that general relativity is failing. In both cases, the singularity is where we meet a quantum theory of gravity. A theory that combines the principles of general relativity with those of quantum mechanics. We call this theory quantum gravity, and despite decades of effort, we do not have it in a complete form. String theory and loop quantum gravity are the two most developed candidates. Each makes progress on some aspects of the problem. Neither is complete. Neither has made a testable prediction that distinguishes it clearly from other theories. But both suggest, in their different ways, that singularities are resolved by quantum effects. In loop quantum gravity, the quantization of space itself creates a minimum volume. You cannot compress matter to literally zero volume. The collapse of a black hole reaches a maximum density and then bounces. There is no singularity, just an extremely dense, hot point from which space-time re-emerges. This has an extraordinary implication. Black holes might not end. They might bounce, producing new spacetime inside them. A new region of spacetime, potentially with different physical constants, budding off from ours and expanding into a new universe. This is the fecund universe hypothesis, associated with the cosmologist Lee Smolin. In this view, black holes are not just features of our universe. They are reproduction events. Each black hole produces a new universe. The physical constants of that universe are slightly different from those of its parent. If there are many universes, and if the physical constants influence the likelihood of black hole formation, then natural selection might apply. Universes whose constants allow the formation of many black holes have more offspring universes, and the constants that allow many black holes might be similar to the constants that allow stars, heavy elements, and life. This is speculation beyond what we can currently test. But it is grounded in physical principles that we take seriously. And it suggests a picture of the cosmos that is almost incomprehensibly larger than what we ordinarily imagine, not one universe, but an infinite tree of universes, each spawned from a black hole and its parent, each with its own constants, its own laws, its own possibilities. We live inside a universe that was itself born from a black hole in a parent universe. We are, in this picture, descendants of a collapse. And every black hole in our universe is potentially a cosmic birth event. Every singularity that we thought was a dead end is actually an origin. This is the deepest version of what I mean when I say that black holes are not just cosmic vacuum cleaners. They are not just where things go to die. They might be where new things come to be born. Death and birth, compression and expansion, the end and the beginning, all wrapped up in the same object, the same mathematics, the same equations. The universe does not run in a straight line from birth to death. It folds back on itself. It is recursive. It creates the conditions for its own continuation. And we are inside that recursion. We are part of the process. Let me try to bring this together and say something about what it means to understand black holes, not just technically but philosophically. Black holes force us to confront the limits of our intuitions. We are evolved for the middle scales of reality, for objects moving at ordinary speeds in gravitational fields far weaker than anything near a black hole. Our intuitions about space, time, identity, and continuity are calibrated for that middle range. Black holes are outside that range. And every time we try to apply our ordinary intuitions to them, we go wrong. We think about someone falling in and freezing at the horizon, and we think, which is real, the freezing or the falling? Our intuition says there must be a fact of the matter. General relativity says both are real, from different perspectives. We think about information destruction and feel that it should be possible. Our intuition says things can just end, be lost, cease to exist. Quantum mechanics says, no. Information is conserved absolutely. Nothing is ever truly lost. We think about the singularity and imagine the end of something. Loop quantum gravity says, no. The singularity is where the next beginning is. At every turn, our intuitions fail and the physics suggests something stranger, something richer, something that does not match our ordinary sense of how things work. And maybe that is the lesson. Not that reality is incomprehensible, but that our ordinary mode of comprehension is too limited. We need to expand. We need to allow the mathematics to take us places that our gut feeling would never lead us. This is uncomfortable. It is also extraordinary. Because the universe that the mathematics is describing is far more interesting than the universe our intuitions would have designed. A universe where information is never lost. A universe where time itself is relative, where there is no single now. A universe where the dimensionality of space is not fundamental but emergent. A universe where black holes are not endings but transformations. A universe where the information that makes you you is preserved even when the physical structure that holds it disperses. This is not the simple universe of common sense. But it might be the actual universe. And living in the actual universe, however strange it turns out to be, seems better than living in a comfortable fiction. Let me tell you about what happens at the event horizon in full detail now, because I think the event horizon is one of the most philosophically interesting places in all of physics, and I want to do it justice. You are in a spaceship, falling freely toward a supermassive black hole. The black hole has a mass of 1 billion suns. Its event horizon is about 3 billion kilometers in radius. You are outside the horizon, approaching. As you fall, you feel weightless. This is because you and your spaceship are falling together. There is no differential force. If you were very close to a stellar mass black hole, the tidal forces would rip you apart before you reached the horizon. But for a supermassive black hole, the tidal forces at the horizon are gentle. You could cross the horizon intact. You look back. The universe behind you is changing. Light from behind you, trying to catch up with you as you fall, is blue shifted. You see the stars ahead, in the direction of the black hole, brightening and shifting. The geometry of your sky is distorting. You cross the horizon. You do not feel it. There is no bump, no jolt, no sensation. You are inside the black hole. But now something extraordinary is happening to space-time itself. The direction toward the singularity, what you would naively think of as the inward spatial direction, has become time-like. Your future is, in every direction you can look, pointed inward. You cannot stop your motion toward the singularity any more than you can stop moving forward in time. You have time left. If the black hole is large enough, you might have hours or even years before the tidal forces become dangerous. You can do physics experiments. You can make measurements. You can think. But you cannot leave. And eventually, the tidal forces will increase as you approach the singularity. They will stretch you along the radial direction and squeeze you in the transverse directions. Physicists call this process spaghettification, which is one of my favorite words in all of science. And then, the singularity, where the math breaks and we stop knowing. Meanwhile, the observer who stayed outside sees something completely different. They watch you approach the horizon. They watch you slow down. They watch your image redshift from visible light to infrared to microwave. You fade. You never cross the horizon, from their perspective. They see you frozen there, growing dimmer. Eventually, they will detect the Hawking radiation from the black hole. It is thermal. It carries no apparent information. But according to the resolution of the information paradox, if there is one, the information about you is encoded in the subtle correlations of that radiation. You are not destroyed. You are encrypted. Both of these descriptions, the infalling observer and the outside observer, are correct. They are related by a transformation that physicists call complementarity. They are complementary descriptions of the same underlying physics, valid from different perspectives, not directly contradictory because no single observer can access both. This is perhaps the deepest thing black holes have taught us, that reality does not have a single description. That different observers, with access to different information, give different but equally valid accounts. And reconciling those accounts requires going to a level of description deeper than either. That deeper level might be the holographic one, the two-dimensional boundary theory that is equivalent to the three-dimensional bulk theory. From the boundary perspective, there is no black hole interior. There is only the dynamics on the boundary, fully unitary, fully information-preserving. The black hole interior is an artifact of the bulk description, a useful fiction that helps the observer inside the horizon make sense of their experience, but not a fundamental feature of the underlying reality. I want to be careful not to overclaim here. This is not established fact. It is the direction that the physics seems to be pointing, the destination toward which decades of work on the information paradox and holographic duality seem to converge. But we do not have a complete theory. We do not have a proof. We have hints and partial results and mathematical structures that suggest this is the right framework. But the hints are extraordinary. The partial results are beautiful. And the mathematical structures, especially Meldesena's duality, have the ring of deep truth even if we cannot yet see the whole picture. So let me end with what I think the most important takeaway is from all of this, the thing that black holes, the information paradox, and the holographic principle, taken together, are telling us about reality. Reality is not what it looks like. That sounds like mysticism. It is not. It is a precise physical claim. The universe as it appears to our senses, three-dimensional, with space and matter and events happening in time, is a description. A valid description. A useful description. But not the most fundamental description. At a deeper level, the physics suggests the universe is informational. It is about relationships, correlations, entanglement. Space emerges from entanglement. Time emerges from entanglement. The three dimensions of our experience emerge from a two-dimensional structure we cannot directly perceive. And information, the fundamental stuff of this underlying reality, is never destroyed. It is transformed. It is encoded. It is scrambled. But it persists. This has a personal implication that I find genuinely moving. Every pattern that has ever existed, every configuration of matter and energy, every thought and every star and every organism, leaves a trace. Not a mystical trace. A physical trace, encoded in the quantum state of the universe. The information is there, scrambled, inaccessible, but real. We are informational beings in an informational universe. And the universe does not forget. I do not know what to do with that, ethically or emotionally. I am not sure any of us do. But I think it matters. I think it says something important about the kind of universe we live in. Not a universe of pure matter, indifferent to pattern and structure, indifferent to the brief flame of consciousness. But a universe that preserves, at its most fundamental level, the fact that we were here, the fact that we happened, the fact that we thought and felt and wondered. The black hole is not just where things go to die. It is where things go to be transformed. And so are we. Every atom will eventually be recycled. Every structure will eventually change. But the information, the pattern, the relationship, the fact of having existed and been particular, that persists. In the Hawking radiation, in the quantum correlations, in the holographic encoding at the edge of the cosmos. We are not permanent, but we are not nothing. In the deepest physics we know how to do, we are not nothing. And the black hole, that most frightening object in the universe, that tear in the fabric of space-time, is the place where we learn this. The place where the crisis of physics, the collision of our two best theories, forced us to think more deeply about reality than we ever had before. And in doing so, showed us something about ourselves. We are patterns in an informational universe that does not forget patterns. We are the universe knowing itself, one black hole at a time. The nature of nothing. Before we go further, let me say something about the vacuum. About nothing. Because understanding black holes requires understanding that empty space is not actually empty, and this turns out to be one of the most consequential facts in all of physics. Classical physics had a clean picture of the vacuum. Empty space was empty. Nothing there. No energy, no fields, no particles. Just pure geometric space waiting to be filled. Quantum mechanics destroyed this picture completely. In quantum mechanics, the uncertainty principle applies not just to particles but to fields. Every quantum field, the electron field, the electromagnetic field, every field in the standard model, cannot have a perfectly defined value of zero everywhere. There is always a quantum fluctuation, an uncertainty, an unavoidable minimum agitation. This means the vacuum, empty space with no particles, has energy. The zero-point energy of all the fields. This is not a small correction. When you try to calculate the energy density of the vacuum from quantum field theory, you get a number that is somewhere between 10 to the 60th and 10 to the 120th power larger than the observed value. This is called the cosmological constant problem, and it is arguably the worst prediction in the history of physics. The theory and the observation disagree by up to 120 orders of magnitude. If I told you I predicted the weight of an apple and was off by a factor of 10 to the 120, you would rightly conclude my theory was completely wrong. And yet quantum field theory works brilliantly for everything else. The disagreement is specifically about the energy density of the vacuum, which the cosmological constant problem is about. Something is canceling most of that vacuum energy. We do not know what. This is one of the deepest unsolved problems in physics. But the vacuum fluctuations themselves are real. The Casimir effect, the spontaneous emission of photons from atoms, the Lamb shift in hydrogen energy levels, all of these are measurable consequences of quantum vacuum fluctuations. They are not theoretical artifacts. They are observed phenomena. And near a black hole, these vacuum fluctuations produce Hawking radiation, as I described. The black hole literally extracts energy from the quantum vacuum, causing the vacuum state near the horizon to produce radiation. This means the black hole is connected to the vacuum. It is not isolated from empty space. It is embedded in it, interacting with it, affecting it. And through that interaction, information that fell in is eventually extracted back out, however scrambled. The vacuum is the medium through which black holes communicate with the outside universe. It is the substrate in which information is preserved. It is the field in which the holographic encoding takes place. Nothing, it turns out, is doing a lot of work. The arrow of time. Let me talk about something that gets at the deepest strangeness of black holes, the arrow of time. The fundamental laws of physics are, with one exception, time-symmetric. The equations of quantum mechanics, of electromagnetism, of general relativity, all look the same whether you run them forward or backward in time. There is no preferred direction of time built into the fundamental laws. And yet we experience time as profoundly asymmetric. The past is fixed and the future is open. Eggs break but do not unbreak. Heat flows from hot to cold and not the reverse. Entropy increases. The arrow of time is one of the most obvious features of our experience. The standard explanation involves entropy and the second law of thermodynamics. Entropy, a measure of disorder, increases with time. But this raises the question, why was entropy low in the past? The answer points to the Big Bang, a state of extraordinarily low entropy, a highly ordered beginning from which the universe has been expanding and disordering ever since. Black holes complicate this picture beautifully. The entropy of a black hole is proportional to the area of its event horizon. A black hole is, in a precise sense, the highest entropy object of its size. When matter falls into a black hole, the total entropy increases. This is consistent with the second law. But now consider, as the black hole evaporates through Hawking radiation, what happens to the entropy? Initially, the entropy of the system, the black hole plus the radiation it has emitted so far, increases. But eventually, if information is preserved, there must come a moment when the entropy of the outgoing radiation starts to decrease. This moment is called the Page time, after the physicist Don Page who calculated it. After the Page time, the entanglement entropy of the radiation starts to decrease, as the information encoded in it becomes accessible. This is strange. The entropy decreasing in a subsystem is not impossible. It happens all the time in small systems, but it requires that the radiation is highly entangled, that there are correlations between early and late radiation that carry information. It requires that the Hawking radiation is not truly thermal, not truly random, but secretly ordered. The arrow of time, and the second law, emerge from the holographic principle in a subtle way that is still being worked out. But the basic message is that black holes are not just passive receptors of entropy. They are dynamic, evolving systems that transform information. And the arrow of time, the forward asymmetry of our experience, is connected to how black holes transform information and how the universe's holographic description encodes the past and future. Wormholes and the geometry of entanglement. There is one more extraordinary idea I need to tell you about, one that has emerged from the intersection of black hole physics and quantum mechanics in the last decade. It goes by the shorthand ER equals EPR, named after two famous papers from 1935. In 1935, Einstein and his colleagues published two papers that seemed to be about completely different things. In one, Einstein and Rosen described a feature of the Schwarzschild solution to the equations of general relativity, a wormhole, a bridge connecting two separate regions of spacetime through the interior of a black hole. These are called Einstein-Rosen bridges. In the other, Einstein, Podolsky, and Rosen described a feature of quantum mechanics that troubled them deeply: quantum entanglement. Two particles can be created in a state where measuring one instantly affects the measurement outcome of the other, no matter how far apart they are. Einstein called this spooky action at a distance. We now know it is real and use it in quantum cryptography and quantum computing. For most of the 20th century, these two papers were seen as addressing completely separate phenomena. Wormholes were a feature of general relativity at the largest scales. Entanglement was a feature of quantum mechanics at the smallest scales. They seemed unrelated. In 2013, Juan Melvicena and Leonard Susskind proposed that they are the same thing. That an entangled pair of particles is connected by a wormhole. That the mysterious non-local connection of quantum entanglement is, geometrically, a bridge in spacetime. ER equals EPR, Einstein-Rosen equals Einstein-Podolsky-Rosen. This is not established fact. It is a conjecture, supported by calculations in specific cases but not yet proven in general. But it has inspired an enormous amount of work, because it suggests something revolutionary about the nature of spacetime. If entanglement is equivalent to geometric connection, then spacetime is built from entanglement. The fabric of space, the connections between points, emerge from the quantum entanglement of underlying degrees of freedom. Space is not fundamental. Entanglement is fundamental. Space is what entanglement looks like at large scales. This would explain a deep puzzle. Why does spacetime have the nice properties it has? Why is it smooth, connected, with consistent geometry? Because the underlying quantum state is highly entangled. Maximally entangled degrees of freedom produce smooth, connected spacetime. Reduce the entanglement and spacetime begins to disconnect, to fragment. Some calculations have made this more precise. There are cases where the entanglement entropy of a subsystem of a holographic theory equals the area of a surface in the corresponding bulk geometry. This is the Ryuta-Kiyanagi formula, one of the most important results in recent theoretical physics. It connects a quantum information quantity, entanglement entropy, directly to a geometric quantity, area. What this tells us is that geometry is information. The spatial structure of the universe, the distances between things, the curvature of spacetime, all of it is encoded in the entanglement structure of the underlying quantum state. And black holes, with their dramatic spacetime curvature, their event horizons, their singularities, are regions of extreme entanglement. The inside and outside of a black hole are connected by entanglement. The Hawking radiation and the interior are entangled in a way that, the ER equals EPR conjecture suggests, corresponds geometrically to a wormhole. This is physics at its most abstract and its most beautiful. But it is pointing towards something real, that space itself, the thing we move through and live in, is not fundamental. It emerges from something more fundamental, something quantum and informational. And if space emerges from entanglement, then by understanding and manipulating entanglement, we might eventually be able to manipulate space itself. This is not a technology we have or will have anytime soon. But conceptually, It suggests that the geometry of the universe is not fixed and given but is generated by quantum relationships that are in principle subject to quantum rules. Black holes are where this emergence is most dramatic, where the entanglement structure becomes so extreme that space-time behaves in ways that violate our ordinary intuitions. They are the stress test of space-time, the place where we learn that what we thought was the most solid and foundational thing, space itself, turns out to be a derived, emergent phenomena. What we are made of. Let me close by bringing this back to you. To us. To what these ideas about black holes and space-time and information say about the nature of beings like us. We are made of atoms. Atoms are made of electrons and nuclei. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks and gluons. Quarks and gluons are excitations of quantum fields. And quantum fields, in the holographic picture, are themselves emergent from something more fundamental on a lower dimensional boundary. At every level of this description, what matters is not the stuff but the pattern. Not the electrons themselves but their arrangement and their relationships. The information, not the medium. Your body is not the same atoms it was 7 years ago. Most of them have been replaced. What makes you you is not the particular atoms. It is the pattern, the information, the relationships between the parts. And the universe preserves information. At its most fundamental level, as best we currently understand, the quantum state of the universe evolves unitarily. Nothing is destroyed. The pattern persists. This does not mean you are immortal. The pattern that is you will eventually disperse, transform, become something else. The atoms will become part of the Earth, then part of the Sun when it expands, then drift into the interstellar medium, then fall into another star, then perhaps eventually cross an event horizon. But the information, the fact of your particular arrangement, is encoded in the quantum state of the universe. When your atoms cross an event horizon, their information is encoded in the Hawking radiation. Scrambled, inaccessible, but not gone. The universe keeps a record. Not a perfect record, not one that can be practically accessed, but a record in principle. The deep past is not lost. It is encrypted in the present. And the deep future, whatever it holds, will carry in its quantum state the encrypted record of everything that came before. We are temporary patterns in a universe that does not delete patterns. We are brief but not nothing. We are local but connected, through quantum entanglement, to everything that has ever been entangled with the quantum fields we are made of. We are, in the holographic picture, projections from a lower dimensional reality that we cannot directly perceive, but that preserves everything about us in its encoding. I find this extraordinary. Not comforting in an ordinary way. Not a promise of personal continuity. But extraordinary in the sense of being more than I would have guessed the universe owed us. We live in a universe that is stranger than we imagined. Stranger than common sense allows. Stranger than the universe our intuitions would have predicted. But also richer. Also more deeply connected. Also more careful with what it contains. Black holes are not monsters. They are not cosmic drains, sucking matter into oblivion. They are transformers, processors, the places where the universe rearranges its information most dramatically. And in that rearrangement, nothing is lost. The darkness at the center of a black hole is not the end of the story. It is where the story is written in a language we are only beginning to learn to read. The universe is a hologram. We are the holograms it is most interested in. And we have just barely started to understand what that means. The mathematical heart of darkness. I want to spend some time on the mathematics, not to intimidate you, but because the mathematics of black holes is where the real beauty lies, and I think you deserve to see it even if only in outline. The key equation is Einstein's field equation. It says, in compressed notation, G equals 8 pi times the gravitational constant times T. G here is the Einstein tensor, which encodes the curvature of spacetime. T is the stress energy tensor, which encodes the distribution of matter and energy. The equation says, matter and energy curve spacetime. Curved spacetime tells matter and energy how to move. This is general relativity in one line. The Schwarzschild solution is the simplest exact solution to this equation. It describes the spacetime geometry outside a spherically symmetric mass. It was found by Carl Schwarzschild in 1916, just weeks after Einstein published general relativity, while Schwarzschild was serving on the Russian front in World War I. He sent the solution to Einstein from the trenches. Einstein was astonished. The Schwarzschild solution contains a special radius, the Schwarzschild radius, where the metric coefficient becomes singular. For the Sun, this radius is about 3 kilometers. For Earth, it is less than a centimeter. These are the radii to which these objects would have to be compressed to become black holes. For a long time, physicists thought the singularity in the Schwarzschild metric at this radius was a physical singularity, a place where reality breaks down. It took until the 1950s and 1960s to understand that it is a coordinate singularity, an artifact of the choice of coordinates, like the apparent singularity at the poles on a map of the Earth. The physics is perfectly well behaved there, the coordinates just behave badly. When you choose better coordinates, the Kruskal-Zachary's coordinates, the event horizon becomes manifestly non-singular. An observer falling through experience is nothing special there. The spacetime is smooth. But the global structure revealed by these coordinates is extraordinary. The Schwarzschild solution actually describes not just a black hole but a wormhole connecting two separate regions of spacetime, an Einstein-Rosen bridge. The other side is a white hole, a region from which nothing can enter but from which things can escape, the time reverse of a black hole. Whether these other regions are physically real is a matter of ongoing discussion. They might be mathematical artifacts of the vacuum solution, eliminated by the presence of actual matter forming the black hole. Or they might be real, connected to another universe through the wormhole interior. The Kerr solution, found in 1963, describes a rotating black hole. It is more complicated, and it describes spacetime that is genuinely bizarre inside the event horizon. There is a ring-shaped singularity, not a point. And around that ring, there is a region where the frame dragging of spacetime becomes so severe that you are forced to co-rotate with the black hole even if you are trying to stand still. This region is called the ergosphere, and it allows an interesting process called the Penrose process. Objects can enter the ergosphere and emerge with more energy than they entered with, extracting rotational energy from the black hole itself. Rotating black holes also have two event horizons. And between them, in a region called the inner Cauchy horizon, causality breaks down. You can see the entire future of the external universe in a finite proper time. Closed time-like curves are possible, paths through spacetime that loop back on themselves, in principle allowing you to visit your own past. Whether the Cauchy horizon actually exists in physical curved black holes, or whether quantum effects destroy it, is an open question. Strong cosmic censorship, a conjecture due to Roger Penrose, says that the Cauchy horizon is unstable and collapses under perturbations. Recent work has complicated this picture. The physics near the Cauchy horizon of a rotating black hole remains poorly understood. And all of this mathematical richness, the Penrose process, the ergosphere, the Cauchy horizon, the possibility of closed time-like curves, emerges from one relatively simple equation, Einstein's field equation, applied to a rotating mass. The mathematics is telling us something about the universe. It is saying that the geometry of spacetime near extreme objects is extraordinarily rich. That there are structures and possibilities in the fabric of spacetime that we have barely begun to explore. And at the heart of this richness, always, is the interplay between information, geometry, and quantum mechanics. When did black holes form? The cosmic history of black holes is itself a remarkable story, connected to the story of how the universe got its current structure. The first black holes probably formed very early, in the first fraction of a second after the Big Bang, when the universe was hot and dense enough that quantum fluctuations could produce regions dense enough to collapse directly into black holes. These are called primordial black holes, and they have been proposed as candidates for dark matter, though current evidence makes this seem unlikely for most mass ranges. Then, as the first stars formed, the most massive ones burned through their fuel in millions of years and exploded as supernovae, leaving behind stellar mass black holes. These early stars, called population 3 stars, were made almost entirely of hydrogen and helium, without the heavy elements that make up most of what we see today. They could be much more massive than modern stars, and their remnants could be the seeds of the supermassive black holes that now sit at the centers of galaxies. Those supermassive black holes grew through billions of years of accretion, consuming gas and dust and stars, occasionally merging with other black holes during galaxy mergers. The most massive known black holes are tens of billions of solar masses, sitting at the centers of the most massive elliptical galaxies. Every large galaxy appears to have a supermassive black hole at its center. Our own Milky Way has one, called Sagittarius A star, with a mass of about 4 million suns. We know it is there because we can track the orbits of stars near the galactic center, stars that are moving in tight, fast orbits around an invisible, massive central object. The orbits are best explained by a massive black hole. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole, the supermassive black hole at the center of galaxy M87, 55 million light-years away. The image showed the shadow of the black hole, a dark region surrounded by the glowing ring of infalling material. It matched the predictions of general relativity to the precision available. In 2022, they imaged Sagittarius A star, a black hole that we orbit, every 225 million years, in our path around the galaxy. We live in a galaxy whose center is defined by a black hole. The structure of the Milky Way, the distribution of its stars, the composition of its gas, has been shaped over billions of years by the presence of this central monster. When Sagittarius A star was active, as quasars are active, it drove powerful jets of material out of the galaxy, heating the intergalactic medium, regulating star formation, shaping the environment in which our solar system eventually formed. Black holes are not incidental to the story of cosmic structure. They are one of the main characters. The personal scale. Let me shift from the cosmic to the personal, because I think the most important thing about black holes is not the physics but what the physics asks of us as human beings. Understanding black holes requires a kind of intellectual courage. It requires being willing to follow an argument to a conclusion that violates every intuition you have. It requires trusting mathematics over common sense, because in this domain, common sense has been demonstrated to be systematically wrong. This is uncomfortable. We like our intuitions. We are attached to our ordinary sense of how space and time work, of what cause and effect mean, of what it means for something to end or to persist. Black holes say, your intuitions are calibrated for the wrong regime. They will mislead you. You have to let them go. This is harder than it sounds. Our intuitions are not just beliefs. They are built into how we perceive and navigate the world. They are part of how we recognize patterns and make decisions. Asking us to distrust them in the domain of extreme gravity and quantum mechanics is asking us to function in a domain where our evolved cognitive tools do not apply. Scientists do this by doing mathematics. The mathematics is the language in which the physics speaks, and it does not care about our intuitions. It simply follows the rules. And when the rules lead to a conclusion that seems impossible, we trust the rules over the intuition. But beyond science, I think there is a broader lesson here. Our intuitions about other domains might also be calibrated for the wrong regime. Our moral intuitions, evolved for small groups of early humans, might not be adequate for the global scale of modern civilization. Our economic intuitions, shaped by scarcity and local exchange, might not be adequate for a global economy with exponential technology. Our political intuitions, shaped by the experience of small-scale governance, might not be adequate for the challenges of coordination at civilizational scale. Black holes are where physics learned to distrust its intuitions. Maybe other domains need to learn the same lesson. What comes after? The far future of black holes is intimately connected to the far future of the universe. As I mentioned, eventually, all black holes evaporate. The last one will be gone in something like 10 to the 100 power years. But even before the last black hole is gone, the universe will be almost entirely empty. The stars will be long dead. Protons may have decayed. The only things left will be black holes, and the quantum vacuum, and the slow evaporation of those black holes. When the last black hole evaporates, what is left? Photons. Neutrinos if they are stable. Electrons and positrons if protons have not all decayed. But at lower and lower energies, more and more spread out, more and more thermalized. Eventually, the universe approaches a state of maximum entropy. Thermal equilibrium. No gradients. No structure. No change. Does time end here? Or does it continue, meaninglessly, with the quantum vacuum continuing to fluctuate? Some physicists have calculated that in a universe at maximum entropy, there is still a tiny but non-zero probability of a fluctuation that produces a Boltzmann brain, a mind that spontaneously assembles from the random motion of particles, experiences a brief moment of consciousness, and then disperses. The number of Boltzmann brains produced in the infinite future would vastly exceed the number of normally evolved minds in the current age of stars. If you found yourself in a universe with both normal minds and Boltzmann brains, you would be vastly more likely to be a Boltzmann brain. But Boltzmann brains would have mostly random, incoherent memories, not the coherent experience of an ordered universe that you actually have. This Boltzmann brain problem is a real headache for cosmologists. It suggests that any theory that predicts an eternal universe with any positive entropy production will eventually be dominated by Boltzmann brains, which contradicts our experience. One resolution is that the universe does not last forever in a state of high entropy. Perhaps there is a quantum transition, some process that resets the entropy, initiates a new cycle. Or perhaps the universe is not eternal in the relevant sense. Or perhaps we are, in some sense, the lucky Boltzmann brains who happen to find themselves in the one coherent region. The anthropic argument, uncomfortable as always. These are genuinely open questions. Physics does not know the answer. And they connect the very local question of our own existence to the very global question of the ultimate fate of the cosmos. We exist in a brief window of cosmic history, between the Big Bang and the heat death, when stars burn and planets support life and minds can develop and ask questions. The universe has been running for 14 billion years. It will run for inconceivably longer. We are a flash, early in the story. Whether that makes us insignificant or precious depends on what you value. I lean toward precious. The gift of ignorance. Let me end with something that I think is underappreciated, the gift of not knowing. We do not know what happens at the singularity. We do not know whether the holographic principle describes our actual universe or only an analogous one. We do not know whether information is truly preserved or whether there is some subtle way in which it is not. We do not know whether black holes are reproduction events for new universes. We do not know whether space-time is truly emergent from entanglement. These are not small gaps in our knowledge. They are fundamental. They concern the nature of space, time, information, and reality itself. And not knowing is, I think, a gift. It means there is still work to do. There are still discoveries to be made. There are still moments ahead, maybe in our lifetimes, when someone will have an insight, will notice a connection, will do a calculation, and will understand something that no human has ever understood before. The universe is not yet fully mapped. The deepest questions are still open. The most important journey is still ahead. Every student of physics who is confused by the information paradox, who feels the vertigo of the holographic principle, who does not quite understand why the inside of a black hole makes time and space swap roles, is not failing to learn something. They are feeling what it is actually like to be at the frontier of human knowledge. The confusion is real. The questions are hard. And the answers, when they come, will be extraordinary. Black holes have given us decades of confusion, paradox, and revision. They have forced us to question our most basic assumptions about the nature of reality. They have resisted easy answers and demanded deep thinking. And in doing so, they have produced some of the most beautiful ideas in the history of science. The holographic principle. The ER equals EPR conjecture. The Beakenstein-Hawking entropy. The information paradox as a bridge between quantum mechanics and general relativity. These ideas are not just technical results. They are glimpses of something profound about the universe, about what it is made of, about what we are made of, about what it means for something to exist and to end and to be remembered. Black holes are where physics went to die and found itself reborn, thinking about reality in a way it never had before. That is what I find most remarkable about them. Not the singularity, not the event horizon, not even the Hawking radiation. The way they make us think, the questions they will not let go of. The invitation they extend to everyone willing to sit with the discomfort of not knowing and keep working anyway. The universe has hidden its deepest secrets in its darkest places. We are still learning to see in that dark. But we are learning. And that is everything. The observational revolution. Let me tell you what it was AC. Truly like to see a black hole for the first time. April 10th, 2019. Simultaneous press conferences in Brussels, Washington, Shanghai, Tokyo, Taipei, and Santiago. The Event Horizon Telescope Collaboration, a global network of radio telescopes spanning the Earth, coordinating observations to achieve a resolution equivalent to reading a newspaper in New York from a sidewalk cafe in Paris. Their target was the supermassive black hole at the center of galaxy M87, 55 million light-years away. A black hole 6.5 billion times the mass of the Sun. What they showed the world was a dark circle surrounded by a bright ring, orange and asymmetric, brighter on one side where material is moving toward us and dimmer on the other. The shadow of the black hole, predicted by general relativity, made visible for the first time. People cried. I am not embarrassed to say this. Scientists who had spent their careers working on the theory of black holes, who had calculated what the shadow should look like, who had built the instruments and analyzed the data, were photographed with tears on their faces. Because there it was. The most exotic object in the universe, the place where space-time ends, made visible by light bending around the abyss. Katie Bauman, the computer scientist who led the development of the algorithm that reconstructed the image from the interferometric data, became famous almost overnight. Her image, staring at a laptop screen at the moment the first picture resolved, captured something genuine, the face of a human being at the moment of seeing something no human had ever seen before. 3 years later, they did it again. Sagittarius A star. Our black hole. The one at the center of the galaxy that we orbit. It is smaller and more chaotic than M87's black hole, harder to image because material orbits and falls in faster. But they got it. Another orange ring. Another shadow. We have now seen 2 black holes. And they look exactly like general relativity predicted. This is what makes the information paradox so uncomfortable. We have confirmed that general relativity works extraordinarily well outside the event horizon. The shadow matches the predictions. The gravitational waves from merging black holes, detected by LIGO and Virgo, match the predictions. Every test of general relativity in the strong field regime has confirmed the theory. So when we say that the information paradox requires something to change at or near the event horizon, we are saying that a theory that has passed every observational test needs to fail in a way we cannot yet directly observe. That is an uncomfortable scientific position. But it is the logical consequence of taking quantum mechanics seriously. And we have equal reason to take quantum mechanics seriously. The two great theories are in tension. One of them, or both, must be revised. The resolution will require an insight that no one has yet had. It will probably require thinking about space-time and information in ways that current physicists have not yet fully imagined. It will be the work of future scientists, future graduate students now in high school or not yet born, who will come at these questions fresh and find the key that their predecessors could not. That is the extraordinary thing about physics at its frontier. The next breakthrough is always possible. It could come tomorrow. It could come from an unexpected direction. It could come from someone who has not yet been trained, who brings a perspective that existing experts do not have. History is full of such cases. Einstein was a patent clerk. Faraday had no university education. Ramanujan learned mathematics from a single textbook and produced theorems that professional mathematicians had not imagined. The universe does not care about credentials. It gives its secrets to those who think carefully and honestly about it. The information paradox is one of the most important unsolved problems in physics. It is waiting for its Einstein, its Faraday, its Ramanujan. Maybe that person is reading this right now. Quantum gravity and the path forward. The path to resolving the black hole paradoxes leads through quantum gravity. We need a theory that seamlessly combines the principles of general relativity with those of quantum mechanics. We have hints. The holographic principle is a hint. The AD/CFT correspondence is a hint. ER equals EPR is a hint. The Bekenstein-Hawking entropy formula is a hint. These are pieces of a puzzle, and they are starting to fit together in suggestive ways. String theory was for a long time the leading candidate for quantum gravity. It naturally incorporates gravity, unifies it with the other forces, and provided the framework in which AD/CFT was discovered. But it has not produced a testable prediction that distinguishes it from alternatives, and the landscape of possible string theory vacua is so vast that some physicists worry it cannot predict anything specific about our universe. Loop quantum gravity takes a different approach, quantizing space-time itself, treating the geometry of space as a quantum variable. It predicts a minimum length, the Planck length, below which the concept of smooth space-time breaks down. It naturally resolves the singularity of the Big Bang and possibly the singularity inside black holes. But it has struggled to incorporate quantum field theory in a natural way and has also not produced unique testable predictions. Causal set theory, twistor theory, causal dynamical triangulations, and other approaches each capture some aspects of quantum gravity while struggling with others. The breakthrough, when it comes, will probably not look exactly like any of these. It will probably be a synthesis, or a radically new perspective that makes the current approaches look like partial views of a larger picture. What we can say with confidence is that whatever the correct theory of quantum gravity is, it must reproduce the successes of both general relativity and quantum mechanics in their respective domains. It must predict the same gravitational waves, the same black hole shadows, the same quantum field theory results that we already know. But it must also resolve the singularities, preserve information, and connect the holographic structure of the universe with the three-dimensional experience we have. That is a tall order. It is probably the hardest scientific problem of our time. But it is not impossible. We have made extraordinary progress in the last century. The next century might see us close the gap. Living with the uncertainty. I want to say something about what it means to live as a thinking being in a universe whose most fundamental properties we do not yet understand. It would be easy to feel unsettled by this. Our models of reality, however successful, are provisional. The two theories we trust most, general relativity and quantum mechanics, are known to be incomplete. The fabric of spacetime might be holographic. The experience of three-dimensional reality might be emergent. Information might be preserved in ways we cannot access. Singularities might be the births of new universes. All of this is deeply uncertain. And yet we go about our lives, we make plans, we love people, we care about things that are happening on human scales in human time. How do we reconcile the cosmic uncertainty with the practical certainty of daily experience? I think the answer is that we do not need to reconcile them. They are different levels of description, valid in different contexts. The uncertainty about quantum gravity does not affect whether you should call your mother or whether this bridge will hold your weight. The holographic principle does not change the ethics of how you treat other people. The cosmic level and the human level are both real. They are both important. And they operate semi-independently. But the cosmic level does, I think, affect how we hold our certainties. When you understand that even space and time are not as fundamental as they seem, that the most solid-seeming features of reality are emergent from something more basic, it becomes easier to hold your other certainties more lightly. To be open to the possibility that you have the wrong model. To be willing to update your beliefs in light of new evidence. This is the epistemic lesson of black holes. Not that nothing is certain, but that certainty is always provisional and always earned through the hard work of checking and rechecking and being willing to be wrong. The physicists who found the information paradox were not failures. They were not wrong to trust general relativity. They were doing the hard work of pushing two great theories against each other and finding where they break. That is how physics progresses. That is how we get from confusion to clarity. The same process applies to any domain where we are trying to understand something genuinely difficult. We build models. We test them. We find where they fail. We try to understand the failure. We revise. We iterate. Black holes are physics at its most honest. They are the place where the models break and the physicists admit it and keep working anyway. That honesty, that persistence in the face of failure, is the most important thing I want you to take from all of this. Not the specific physics, though that is extraordinary, but the model of how to engage with hard problems. How to face the edge of your knowledge without flinching. How to live with uncertainty while still caring about getting things right. That is the lesson of the event horizon. You can go up to the edge of what you know. You can look into the dark. And you can keep thinking. That is enough. That is actually everything. The last light. I want to close with an image that I find haunting and beautiful in equal measure. Somewhere in the universe, right now, the last photons from an old star are falling into a black hole. They cross the event horizon. They are incid. They spiral toward the singularity. From outside the black hole, they are never seen to cross. They hover at the horizon, redshifting, fading, becoming part of the soft Hawking glow. From inside, they travel inward. The singularity is their future. There is no avoiding it. The information they carry, the specific wavelengths and polarizations that encode the last moments of a dying star, is not destroyed. It is encoded in the quantum state of the Hawking radiation, spread across photons that will drift outward for trillions of years. The star is gone. The light is gone. The black hole that swallowed them will eventually evaporate, leaving nothing behind but a faint thermal memory in the structure of the vacuum. And yet, the information persists. In the deep quantum correlations of the outgoing radiation. In the holographic encoding of the universe. In the mathematical structure of the quantum state. The universe does not forget. That star happened. Those photons carried their message. The information exists. And on one small planet, orbiting one ordinary star, in one of 2 trillion galaxies, creatures made of the remnants of ancient stellar explosions built instruments precise enough to detect the gravitational waves from black holes merging 1 billion light-years away. And then they sat down to think about what it all means. We are those creatures. We are the universe's attempt to understand itself. And the black hole, the most extreme and most mysterious object in the cosmos, is the place where that understanding runs deepest and is most challenged. The edge of everything is not a wall. It is a question. And we are still answering. The journey inward continues. Through the event horizon, toward the singularity, into the place where mathematics fails and new mathematics must be born. We are going there. Not physically, but intellectually. With equations and observations and arguments and the kind of persistent, stubborn curiosity that is the best thing about being the kind of creature we are. Black holes are not the end of the map. They are the place where the next map begins. And we are drawing it. One calculation at a time. One observation at a time. One insight at a time. In the dark, finding the light. The paradox of the paradox. There is something I want to say about paradoxes in general, because the black hole information paradox is not unique in kind, only in degree. Physics has a long history of productive paradoxes. The ultraviolet catastrophe, the prediction that a hot body should radiate infinite energy at short wavelengths, led to quantum mechanics. The apparent contradiction between Newtonian mechanics and Maxwell's electrodynamics led to special relativity. The incompatibility of special relativity with Newtonian gravity led to general relativity. In each case, the paradox was not a sign that physics had failed. It was a sign that physics had succeeded in finding the edge of its current framework, and that the resolution would require a new framework that extended beyond the old one. The information paradox is the same kind of beast. It is not a failure of physics. It is physics finding the edge of its 2 greatest theories simultaneously and demanding something new. The new thing might be as different from quantum mechanics and general relativity as quantum mechanics is from classical mechanics. It might require concepts we do not yet have words for. It might require mathematical structures that do not yet exist. It might require a revision of ideas as fundamental as what we mean by space, time, and information. That is an enormous ask. It is also an enormous opportunity. Every generation of physicists has faced its version of this moment, the moment when the existing framework is clearly insufficient and the new one has not yet arrived. The students who were trained in classical mechanics in 1895 were doing rigorous, precise, beautifully successful physics. But they were working in a framework that was about to be revolutionized. Within 20 years, relativity and quantum mechanics had transformed the foundations of the field. We may be at such a moment now. The students currently learning general relativity and quantum field theory are mastering frameworks that are extraordinarily powerful and successful. But both frameworks are known to be incomplete, and the completions are not yet in hand. The next revolution might come from one of these students. From someone who has absorbed both frameworks deeply and found, in the tension between them, the seed of a new synthesis. This is not a guarantee. Scientific revolutions cannot be forced. They happen when someone has the right combination of knowledge, creativity, and readiness to challenge the foundations. You cannot schedule an Einstein, but you can create the conditions that make one possible: rigorous education, open scientific culture, willingness to take unconventional ideas seriously, funding for basic research that might not have immediate applications. These are the things that matter for long-term scientific progress. Not just for understanding black holes, but for the continued development of physics at its frontier. Gravity as thermodynamics. Let me tell you about one more extraordinary idea that has emerged from the study of black holes, the possibility that gravity itself is thermodynamic in nature. In the 1990s, Ted Jacobson derived Einstein's field equations from thermodynamic principles. He showed that if you assume that the entropy of any local patch of spacetime is proportional to its area, and if you assume the first law of thermodynamics applies to local patches, then Einstein's equations follow as an equation of state. Gravity, in this view, is not a fundamental force. It is an emergent phenomenon, like the pressure of a gas, arising from more fundamental microscopic degrees of freedom. This is a remarkable result. Einstein's equations, the most successful description of gravity we have, derivable from thermodynamics alone. It does not tell us what the underlying microscopic degrees of freedom are, but it suggests that they exist and that spacetime is their thermodynamic limit. Eric Verland extended this idea into what he calls emergent gravity. He proposed that gravity is an entropic force, arising from the tendency of systems to maximize entropy. When you hold an object above the floor, you are fighting not just gravity but the tendency of the quantum information in the system to spread out. Gravity is the name we give to this entropic tendency. This sounds strange. We are used to thinking of gravity as a fundamental interaction, on par with electromagnetism and the nuclear forces. The idea that it might instead be an emergent phenomenon, like temperature or pressure, is counterintuitive. But consider, we do not think temperature is a fundamental interaction. We know it emerges from the average kinetic energy of atoms. When we see a hot object radiate heat, we do not look for a fundamental force of heat transmission. We explain it in terms of more fundamental processes. Maybe gravity is similar. Maybe what we call gravity is the macroscopic consequence of some microscopic dynamics of spacetime, something that becomes apparent at large scales but emerges from quantum degrees of freedom at small scales. If this is right, then quantizing gravity is the wrong approach. Quantum gravity is not gravity plus quantum mechanics. It is the underlying quantum theory from which both spacetime geometry and its thermodynamic interpretation as gravity emerge. This is a genuine minority view in physics. Most physicists working on quantum gravity believe gravity is fundamental and must be quantized. But the thermodynamic approach has produced real results, and the emergent gravity program has gained traction. The truth is probably more nuanced than either camp currently believes. The universe rarely divides cleanly into fundamental and emergent at a single level. There are multiple levels of description, each emerging from the one below, and the question of which level is fundamental often turns out to be frame-dependent. What we can say is that black holes, by providing a context in which thermodynamic properties of spacetime become visible and measurable, have been central to the development of these ideas. Without black holes, and without Hawking's discovery of black hole radiation, the thermodynamic interpretation of gravity might never have become concrete enough to work with. Black holes are not just interesting objects. They are the laboratory in which the deepest questions about the nature of spacetime are being tested. Time, black holes, and the present moment. I want to end with something personal, something that I think about when the physics becomes too abstract. You are reading this at a specific moment. There is light entering your eyes, converted to nerve signals, processed by your brain. There is memory of the previous sentence, anticipation of the next paragraph. There is a sense of being embedded in time, flowing forward, experiencing the present. From the perspective of black hole physics, this experience is strange. There is no universal present. Different observers moving at different speeds and in different gravitational fields have different present moments. The past and future are, in some sense, equally real, just inaccessible from where you are. And yet you have this experience of nowness, this acute sense of the present moment, this feeling of being here, at this point in time. Physics does not fully explain this. Consciousness is not understood. The relationship between the physical description of the universe, in which all times are equally real, and the experience of a present moment, is one of the deepest unsolved problems in philosophy and science. Black holes make this problem more vivid. Inside the event horizon, the future becomes a place in the same way that locations are places in. They spiral toward the singularity. From outside the black hole, they are never seen to cross. They hover at the horizon, redshifting, fading, becoming part of the soft Hawking glow. From inside, they travel inward. The singularity is their future. There is no avoiding it. The information they carry, the specific wavelengths and polarizations that encode the last moments of a dying star, is not destroyed. It is encoded in the quantum state of the Hawking radiation, spread across photons that will drift outward for trillions of years. The star is gone. The light is gone. The black hole that swallowed them will eventually evaporate, leaving nothing behind but a faint thermal memory in the structure of the vacuum. And yet, the information persists. In the deep quantum correlations of the outgoing radiation. In the holographic encoding of the universe. In the mathematical structure of the quantum state, the universe does not forget. That star happened. Those photons carried their message. The information exists. And on one small planet, orbiting one ordinary star, in one of 2 trillion galaxies, creatures made of the remnants of ancient stellar explosions built instruments precise enough to detect the gravitational waves from black holes merging 1 billion light-years away. And then they sat down to think about what it all means. We are those creatures. We are the universe's attempt to understand itself. And the black hole, the most extreme and most mysterious object in the cosmos, is the place where that understanding runs deepest and is most challenged. The edge of everything is not a wall. It is a question. And we are still answering. The journey inward continues. Through the event horizon, toward the singularity, into the place where mathematics fails and new mathematics must be born. We are going there. Not physically, but intellectually. With equations and observations and arguments and the kind of persistent, stubborn curiosity that is the best thing about being the kind of creature we are. Black holes are not the end of the map. They are the place where the next map begins. And we are drawing it. One calculation at a time. One observation at a time. One insight at a time. In the dark, finding the light. The paradox of the paradox. There is something I want to say about paradoxes in general, because the black hole information paradox is not unique in kind, only in degree. Physics has a long history of productive paradoxes. The ultraviolet catastrophe, the prediction that a hot body should radiate infinite energy at short wavelengths, led to quantum mechanics. The apparent contradiction between Newtonian mechanics and Maxwell's electrodynamics led to special relativity. The incompatibility of special relativity with Newtonian gravity led to general relativity. In each case, the paradox was not a sign that physics had failed. It was a sign that physics had succeeded in finding the edge of its current framework, and that the resolution would require a new framework that extended beyond the old one. The information paradox is the same kind of beast. It is not a failure of physics. It is physics finding the edge of its 2 greatest theories simultaneously and demanding something new. The new thing might be as different from quantum mechanics and general relativity as quantum mechanics is from classical mechanics. It might require concepts we do not yet have words for. It might require mathematical structures that do not yet exist. It might require a revision of ideas as fundamental as what we mean by space, time, and information. That is an enormous ask. It is also an enormous opportunity. Every generation of physicists has faced its version of this moment, the moment when the existing framework is clearly insufficient and the new one has not yet arrived. The students who were trained in classical mechanics in 1895 were doing rigorous, precise, beautifully successful physics. But they were working in a framework that was about to be revolutionized. Within 20 years, relativity and quantum mechanics had transformed the foundations of the field. We may be at such a moment now. The students currently learning general relativity and quantum field theory are mastering frameworks that are extraordinarily powerful and successful. But both frameworks are known to be incomplete, and the completions are not yet in hand. The next revolution might come from one of these students. From someone who has absorbed both frameworks deeply and found, in the tension between them, the seed of a new synthesis. This is not a guarantee. Scientific revolutions cannot be forced. They happen when someone has the right combination of knowledge, creativity, and readiness to challenge the foundations. You cannot schedule an Einstein. But you can create the conditions that make one possible: rigorous education, open scientific culture, willingness to take unconventional ideas seriously, funding for basic research that might not have immediate applications. These are the things that matter for long-term scientific progress. Not just for understanding black holes, but for the continued development of physics at its frontier. Gravity as thermodynamics. Let me tell you about one more extraordinary idea that has emerged from the study of black holes: the possibility that gravity itself is thermodynamic in nature. In the 1990s, Ted Jacobson derived Einstein's field equations from thermodynamic principles. He showed that if you assume that the entropy of any local patch of spacetime is proportional to its area, and if you assume the first law of thermodynamics applies to local patches, then Einstein's equations follow as an equation of state. Gravity, in this view, is not a fundamental force. It is an emergent phenomenon, like the pressure of a gas, arising from more fundamental microscopic degrees of freedom. This is a remarkable result. Einstein's equations, the most successful description of gravity we have, derivable from thermodynamics alone. It does not tell us what the underlying microscopic degrees of freedom are, but it suggests that they exist and that spacetime is their thermodynamic limit. Eric Verland extended this idea into what he calls emergent gravity. He proposed that gravity is an entropic force, arising from the tendency of systems to maximize entropy. When you hold an object above the floor, you are fighting not just gravity, but the tendency of the quantum information in the system to spread out. Gravity is the name we give to this entropic tendency. This sounds strange. We are used to thinking of gravity as a fundamental interaction, on par with electromagnetism and the nuclear forces. The idea that it might instead be an emergent phenomenon, like temperature or pressure, is counterintuitive. But consider, we do not think temperature is a fundamental interaction. We know it emerges from the average kinetic energy of atoms. When we see a hot object radiate heat, we do not look for a fundamental force of heat transmission. We explain it in terms of more fundamental processes. Maybe gravity is similar. Maybe what we call gravity is the macroscopic consequence of some microscopic dynamics of spacetime, something that becomes apparent at large scales but emerges from quantum degrees of freedom at small scales. If this is right, then quantizing gravity is the wrong approach. Quantum gravity is not gravity plus quantum mechanics. It is the underlying quantum theory from which both spacetime geometry and its thermodynamic interpretation as gravity emerge. This is a genuine minority view in physics. Most physicists working on quantum gravity believe gravity is fundamental and must be quantized. But the thermodynamic approach has produced real results, and the emergent gravity program has gained traction. The truth is probably more nuanced than either camp currently believes. The universe rarely divides cleanly into fundamental and emergent at a single level. There are multiple levels of description, each emerging from the one below, and the question of which level is fundamental often turns out to be frame-dependent. What we can say is that black holes, by providing a context in which thermodynamic properties of spacetime become visible and measurable, have been central to the development of these ideas. Without black holes, and without Hawking's discovery of black hole radiation, the thermodynamic interpretation of gravity might never have become concrete enough to work with. Black holes are not just interesting objects. They are the laboratory in which the deepest questions about the nature of spacetime are being tested. Time, black holes, and the present moment. I want to end with something personal, something that I think about when the physics becomes too abstract. You are reading this at a specific moment. There is light entering your eyes, converted to nerve signals, processed by your brain. There is memory of the previous sentence, anticipation of the next paragraph. There is a sense of being embedded in time, flowing forward, experiencing the present. From the perspective of black hole physics, this experience is strange. There is no universal present. Different observers moving at different speeds and in different gravitational fields have different present moments. The past and future are, in some sense, equally real, just inaccessible from where you are. And yet you have this experience of nowness, this acute sense of the present moment, this feeling of being here, at this point in time. Physics does not fully explain this. Consciousness is not understood. The relationship between the physical description of the universe, in which all times are equally real, and the experience of a present moment, is one of the deepest unsolved problems in philosophy and science. Black holes make this problem more vivid. Inside the event horizon, the future becomes a place in the same way that locations are places in